Welcome to this video on confidence intervals. This is a slightly longer video, but it's an important topic as confidence intervals are the main tool of statistical inference. They are everywhere, and our objective is to understand what they are and how to interpret them. To do so, I will talk about why we have them and how they work. What's the behaviour of them? So, to properly understand confidence intervals, you'll need to first of all understand sampling variation and sampling distributions. But if you watch those videos and have understood them, then I'm sure you'll get a grip of confidence intervals, as in essence, no new ideas are introduced here. So, let's just remind ourselves of what we already know, and you've heard it many times. In statistical inference, we take a sample or do an experiment, and we try to infer or draw conclusions about the entire population based on what we've observed. Typically, we want to estimate a population parameter. That parameter could be anything, the mean, the relationship between two quantities, etc. But we've collected only a sample, or only several replicates of an experiment. As we saw in previous videos, if we've done a good experiment, or we've done a good study and got a random sample from the target population and haven't introduced systematic bias into our estimate, then in a hypothetical world of repeated sampling, our estimate of the population parameter would be expected to vary in a random way around the true population parameter, as captured by the sampling distribution, shown here. So this means that we may have been lucky and have hit the nail or the parameter right on its head, or we may have been unlucky and hit our fingers, or even more unlucky and hit someone else's fingers and been some way away from the parameter. But the key thing to bear in mind is we will never know because we don't know the true value, and we tend to only do one study or one experiment. So the estimate on its own is not too helpful. For example, here is a point estimate from a study looking at the reduction in risk of preeclampsia using low-dose calcium supplementation. So we see a 90% reduction in risk. Now that looks impressive. It's suggesting that low-dose calcium supplementation almost wipes out the risk of preeclampsia. However, it's just a point estimate, and we've already seen when discussing sampling distributions that these estimates are prone to random variation just from sampling. What would be more helpful is if we can communicate a range of values that we're confident contains the true value, or some way of including how close we think our guess could be based on our study or experiment. And that is what a confidence interval does. And we can select the degrees of confidence in our guess. Often we use something called a 95% confidence interval. So here's the 95% confidence interval for this particular study. You can see that the confidence interval has a lower limit and an upper limit. So it's based on two numbers and they're called the limits. Now, instead of saying calcium is the panacea of all preeclampsia, we're now saying that calcium is inconclusive. We can't even be confident that it won't actually also cause any harm. So the study was not able to produce a very precise estimate. You cannot draw any conclusion with respect to the effect of supplementation from it. Now here's a second study. The point estimate here shows a smaller effect compared with the first study. It's minus 60% or a 60% reduction in preeclampsia. But the confidence intervals are more narrow. In this one we can be confident that there's some benefit. And we're confident that true benefit lies somewhere between 20% and a 73% reduction in risk of preeclampsia. So the lay interpretation of a 95% confidence interval that we've just been using is this. So a 95% confidence interval gives a range of values from which we're 95% sure contain the true value. A more statistical definition describes the behaviour of a confidence interval over repeated random samples. So here, a range of values that we'd expect to capture the true population value 95% of the time. So that's saying if we did this study 100 times, repeat sampling, and estimated a confidence interval each time, we'd expect 95 of those confidence intervals to contain the true value. An incorrect, but unfortunately commonly used interpretation is to flip the probability around and attach it to the population value. So that would be saying that there's a 95% probability that the true value lies between these limits. It's wrong. So let's deal with the statistical inference side of things. First of all, we do not know the true parameter, but it is assumed to be fixed, to take on one value. So a true value is either inside the confidence interval or it isn't. There's no probability involved with the true value other than 0 or 1. It's definitely not in there, or it definitely is. It's a fixed value. The probability is whether the confidence limits contain the true value. Sometimes they will, sometimes they won't, and that's due to sampling variation. For a 95% confidence interval, 95% of the time we think they will. So this idea of this holy true value might sound a bit like a doctrine, something you have to believe in rather than something that's rational, but that's just a reflection of the way that we do inference. So let's look at how that inference works, and to do so we need to look at the basic form of a confidence interval. So here this is for a 95% confidence interval, and you can see that it's the point estimate or statistic calculated from our sample plus or minus 1.96 times the standard error or the standard deviation of the sampling distribution. So why the 1.96? Well, that's called the confidence coefficient, and that number differs depending on how confident we want to be. And we'll go into more detail in another video when we talk about the normal distribution a lot more. But for now, there is a link to this, to what we've already done. If you can remember the 3 sigma rule, or the 68, 95, 99.7 rule, that rule says that for normally distributed variables, 95% of the values would be expected to fall within 2 standard deviations of the mean. But that rule also applies to sampling distributions that are assumed to be normal too. So we expect 95% of our point estimates to fall within plus or minus 2 standard deviations of the sampling distribution. But this is the important part of the calculation to allow you to understand what a confidence interval is. It's a point estimate. And we know that all point estimates are subject to sampling variation, all of them. So let's look at a sampling distribution again to see what this means for our confidence intervals. So to illustrate, we need to imagine we know the true population parameter that we're trying to estimate. So let's say we know the mean height in a population of male students to be 180 centimetres. So that's a population parameter, and we know what it is. It has a standard deviation of 10 centimetres. And what if we take samples of size 16 to get a point estimate of this parameter? So our point estimate would be the sample mean. What would that sampling distribution look like? Well, first of all, we need to calculate the standard error of the mean, which is 2.5 centimetres. So we can now draw the sampling distribution. So let's put the units in units of standard error to orientate ourselves. So the sampling distribution is a distribution of point estimates from repeated sampling. So if I go out and take a sample of 16 students, then I might get a value for a sample mean of 182.5. If I go out again, I might get a sample mean this time closer to the population value of 180. And I keep sampling and sampling like that. Eventually, I'd expect a distribution to appear. And I'd expect that distribution to be normally distributed, and the mean of that sampling distribution to be equal to the population parameter mu. So we can use the 3 sigma rule to orientate ourselves. So I'd expect 95% of my point estimates from repeat sampling to be within plus or minus 2 standard errors of the true population mean. So about 95%. And I'd expect the majority of my sample means from repeated sampling to be within plus or minus 1 standard error. So here, from using the 3 sigma rule, we'd expect 68% of our sample means from repeated sampling to fall within plus or minus 1 standard error of the true population value. So if we went out and got a sample, we could be here, we could be here, we could be here, we could be anywhere, we could be even all the way out here, but we never know what this true population parameter is, how far away we are. We have no reference point. All we do is we just look out from our point estimate here. That's the boat that we're sitting in, and we look out in front and we look out behind, but we've no idea where this true value is. It could be behind us or it could be in front of us. So what do we know, or what can we use to help give us a feeling for whether our estimate here or our estimate here or wherever it ends up, to give us a feeling for whether it's any good or not? Well, if we assume that our sampling distribution is like this one here, which is normal, let's just get rid of those squiggles, replace it with another squiggle, and it's a pretty good assumption, as we'll see in later videos, then we know that 95% of our sample means will be within 2 standard errors of the true value, even if we don't know where that true value is. So if we're in a sample mean and we reach out 2 standard errors from it, so we reach out 2 standard errors in front and 2 standard errors behind, so in our example that's 5 centimeters either side, we'd expect 95% of the time to catch the true mean. So for example, if we're here within the 95% range and we reach out 2 standard errors in front and behind, we capture the true population value. And I heard this name for a confidence interval. A confidence interval is a parameter catcher. That's exactly what it is. We don't know whether we've caught it, but we're on 95% of the time we think that we will catch the true parameter. But what if our point estimate is more than 2 standard errors away from the true population value? Well then, we don't catch a population parameter, but we'd only expect to get a point estimate this far away from the true population value 5% of the time. When this happens, we've got a bad confidence interval, but we do not know when it has happened. Hence we use the word confidence when interpreting the confidence interval. We're 95% confident that the confidence limits contain the true value. And importantly, you can see that because our confidence interval is attached to our point estimate, which varies due to sampling, then so too will the confidence interval vary over repeated samples. So the confidence intervals are subject to sampling variation, and sometimes we will not capture the true value, but with a 95% confidence interval, on only 5% of occasions from repeated sampling would we expect not to capture the confidence interval. This is the behaviour of a confidence interval. So this is what a set of confidence intervals would look like from 100 repeated and independent random samples of sample size 16 to estimate mean height in the example we've just been discussing. So the population mean is here, and you can see that out of 100 random samples, on 5 occasions or 5% of times, the confidence intervals did not capture the true mean. So that is the long run behaviour of a confidence interval. So what factors can affect a confidence interval? Well, there are 2 main factors to understand. As we saw, a confidence interval is based on the standard error, so anything that affects the standard error would affect the width of a confidence interval. We had a look at that in the video on precision and bias. In particular, it's things that affect the precision. And the key aspect was that smaller samples or smaller studies have wider confidence intervals because our point estimate lacks precision or will have a lot of sampling variation. So we'd have to have a wider confidence interval to be confident of capturing the true value. The level of confidence we use will affect the confidence interval. If we want to be 99% confident of containing the true value, then we'll have to throw our arms wider to get the true value. Likewise, if we're not so fussed about being wrong, then we could choose a lower limit, 90% say, and our confidence interval would be more narrow. We'll show how to calculate these in later videos, but when we report a confidence interval, we should always state the confidence level. So hopefully you've learned that confidence intervals are really useful and how to interpret them. They're parameter catchers. We don't know if they contain the true population value. And confidence intervals can be estimated for almost any statistic we choose. So here's a few examples. But most importantly, they should always be reported if possible. So we've talked a lot about interpretation. This table is just a summary of the different ways in which we've been interpreting a confidence interval. So you might want to pause this and have a look if you wish. And lastly, a joke. If you understand this joke, then you've understood confidence intervals. So if you laugh or sigh, it's a sign that you've understood it. And here's the terms that we've introduced in this video.